Thank you very much for the warm welcome. Thank you for spending your time to come listen to this talk. We're going to be going through the journey I went through of writing a machine learning set of models in competition with some expert system models during my dissertation. And what I really want to convey is my experience going into the project, my experience going through the project, and what I've come away from it with now it's all finished. So, we're going to start off by explaining what groundwater arsenic pollution is. And this might seem like an odd place to start, but we have to start somewhere. So, it's a worldwide thing. If you stick a tube into the ground and water comes in, you start drinking that water, most places in the world there's a risk that it will be polluted with arsenic. And if we look at this map of Bangladesh on the right, we can see this is color-coded for the mean arsenic concentration for different data points which were taken from real wells. So 10 is the UNICEF safe limit, I believe. I really hope it's UNICEF and I'm not picking the wrong name out of the air. But anyway, and then when you get to 50, that's another threshold. But some of these bad boys go right up to the triple digits. So that's not good. What can we do about it? This project, iArsenic, came along, and it said, what we're going to do is we're going to make a model, and you're going to be able to fill data in about your well, and it will tell you, based on the information that an expert would use to decide whether or not it might be safe to drink from, this model will tell you if it's safe to drink from or not. Probably. So there's just a few graphics here, some regional names to kind of, get you grounded, and just that graphic to show the spread of the data set and how much data there is. There was about 800,000 data points in the cleaned final data set. So we've said this is a worldwide problem. Why is Bangladesh particularly badly affected? And there's more about this in the handout. You could have a whole talk about this by itself, but around the 1980s, there was it wasn't UNICEF, I did get it wrong earlier, it was the WHO. So I'm just going to say either the WHO or UNICEF, I'm pretty sure it was UNICEF, in the 80s, set a goal to get, I think it was 90% of Bangladesh population access to clean drinking water by the year 2000. And they kind of did it by installing all of these tube wells, but there was a kind of insidious problem with these tube wells where they weren't installed deep enough and they were tapping into polluted arsenic concentrations. So that picture is, I got it from a Google Drive from Dr. Mohammed Haq at the University of Portsmouth, who was the initial visionary for this project, and I'm pretty sure he took the photo, but I haven't asked him, so that's a real one out in the wild. That's what they look like. So, I knew about this project before. I worked on it a little bit as a research assistant in my second year of university, and we were really bringing the models into the browser, which was awesome because they were originally written in R, and then we got to write them in JavaScript, which might sound a little bit like, oh, wouldn't you so much rather be using Python or something like that? And yes, but the fact that you could get these models to run in the browser with JavaScript, I think, was really something. Anyway, that's a complete tangent. I looked at this project and I thought I can bring a lot to this. And there was a really interesting, I don't know if you call it an article or a paper, but it's like 2 A4 sheets long right here. Oh no, we've gone too far forward. Machine Learning in Earth and Environmental Sciences. This was published in Nature, and it basically says, do geoscientists not have enough machine learning knowledge, and are they unable to tap into the potential of machine learning and black box models because there's not enough knowledge in the field of how they work. So I said I'm going to dedicate a whole year to developing and exploring these machine learning based models, and then we can see how they stack up to the existing models, and maybe we can answer the question like, are we missing out? Or yeah, and in my head, I was like, I know how to do this. If you Google how to make a predictive model in Python, the first thing that comes up, 6 steps. It's so simple. You take your data, you split it into your test train, you train the model on the training data, and then guess what? You test the model on the testing data. You've made a machine learning model. It is that simple. Or so I thought when I was going into my final year of uni. I later found out it's not actually that simple. That machine learning is actually quite complicated. But anyway, this is how I thought you did it. I thought there were these fundamental core attributes that go into a machine learning model, and I could bring these to iArsenic. So the iArsenic model, like I say, it broke all of these rules. It didn't have a test train split. It didn't have any of these things. It was just like a flowchart where Dr. Mohammed Hock, the original visionary of this, did some research, made some decision boundaries. For example, is the well greater than 15 meters deep? And then would base predictions on that. But there's no evaluation of this. It's not even being, well, it's producing predictions on data that the model was trained on, because it does train the data to get some information, like, given a well, what are the wells around it like? And that comes from the data. So there's an element of machine learning, but really it's just a very sophisticated expert system. And I thought, if nothing else, we could come in here and instead of picking these decision boundaries like 15 meters, a machine learning algorithm could statistically find the optimal decision boundaries to make these decisions. So I thought I was guaranteed to beat these expert system models if I just implement them how they already exist, but with this statistical decision boundary identification instead of this research-based one. No spoilers, but it wasn't actually that simple. So the first thing we had to do was evaluate the iArsenic models, and I was like, oh, you get your training set, you get your testing set. Oh no, oh wait. This model, the expert system models, required features which weren't in the original dataset to produce a prediction. And I came up to this like, they've got it wrong in another way. But they hadn't really. And this is actually one of the big benefits of expert systems against machine learning systems, where you can stipulate that information is required that doesn't exist in the training set or the original data set entirely. You just can't do that in machine learning systems because the model will see a feature that it's never seen before because it's not in the original data set, and then it doesn't know what to do with it. Whereas with this, in the actual implementation, when you go to the iArsenic website, the use case is that you have a well in front of you, and therefore, it was the staining data. I think I forgot to mention that. The staining on the well, you can see this one's stained a little bit red, and they can either be stained or black. Stained red or stained black, like this one's stained black. So yeah, it's a benefit of the expert system, not a negative thing, that you can get this data without it being the original data set. But I went into this thinking, okay, what a sin, whatever. So we have to make an evaluation, and when there's a missing data point that the model needs to produce a prediction, you have three choices. You can remove that feature entirely, you can remove the missing data points, so just like the rows in your CSV file, or you can just make the data up. You can impute it, is the term for that, and you do that as an educated guess. In this case, the model needed the feature to run, the staining, and none of the data points had this feature. So the choice was made for me. We had to impute it. So I said, okay, it's either going to be red or black, and this is what the accuracy came out like. So you can see when you use staining red, shown in blue, you get this much accuracy. When you use staining black, shown in orange, you get this much accuracy. And this is a bit of a tangent, but I want to make a point about how accuracy doesn't paint the whole picture. Because you think to yourself here, well, with defaulting to black staining, you think, oh, that's not bad. It's got about 60% accuracy. But then when you look closer and you look at the sensitivity and specificity, the definitions of which I've written down here because you can never remember which way around they go, you can see the specificity is very high and the sensitivity is very low. The sensitivity is the percentage of correctly positive predicted data points. So what this basically means when the specificity was all the high up and the sensitivity was all the way down to the specificity is the percentage of correctly identified negative data points, it's just guessing negative the whole time, guessing that the well is safe to drink every time. So although it's got 60% accuracy, that's not intelligent prediction behavior. And then when we look with red, we found that the sensitivity and specificity were actually quite high. And then I don't want to jump into explaining a confusion matrix because I don't think we have time, but for those of you who can read the confusion matrix, this is the best performing expert system model we found. And this was a shock. This is when I stopped thinking, oh wow, they don't know what they're doing, and thought, they're identifying the false, truly false data points 85% of the time, and the truly true data points 81% of the time. And I was like, I don't know if I expect my models to get that good. So that's when I started to think, I don't really know if I am going to jump in and beat this thing. So if I was going to jump in and beat this thing, I had to start grappling with the question, how good is good enough for my model to replace the models in the web page, which is currently producing the predictions? So we know that they were about, from the bar charts earlier with the accuracy, 81% true positive rate, 85% true negative rate. We know they were pretty good, so we at least need to do better than that, right? But if we never had this expert system, and I was still confident that I could produce a predictive model that could do this job, fill this role, how good would it need to be? And so I've kind of got a thought experiment here. Imagine we've got this magic model, and you don't need to understand the code. If you can, great, but if you can't, no worries whatsoever. I'm just going to tell you what this is doing. You give it a data set, which is represented by this df, and you give it an accuracy. And then this model will look at every data point on the data set, and if the accuracy is like 51%, then 51% of the time it will look at the answer in each data point and agree with that. And then 49% of the time it will disagree. So we've artificially made a model, and we're going to see how it performs with that situation. So I put 51% accuracy through this magic model. And then I said, okay, our true positive count, we correctly identified that 200,000 of the wells, approximately, are not safe to drink from, and 242,000 are safe to drink from. Now, we had a false negative count where we said it was safe to drink from when it wasn't, of 193,000, which is bad. And a false positive count where we said it wasn't safe to drink from when it was, of 233,000, which is also bad. But on the whole, we made more correct predictions than we did incorrect predictions. So, if we roll this out and everyone agrees to adhere to it, then we're going to be helping 16,000 people out, right? And in reality, the margins aren't even this fine. The model was between 81 and 85, on average 83.7% accurate. So the net benefit is actually 585,000. And in my mind, I'm thinking, the barrier we have here to telling 329,000 people that their wells are correctly not safe to drink from is how many people can we tell that it is safe to drink from when it isn't? Like, we want this positive change, but what is it worth? And that's something that you just, I don't think you can figure it out. I think you need an expert to come in and make these decisions in a sensible and informed way as a person that people can trust, or an institution or whatever. The problem with this methodology where we say 51% accuracy is good enough is that we're basically saying every time we're correct, that's +1 on the ethicsometer, if you will, and every time we get it wrong, that's -1. And then we look at this net benefit and we say brilliant. But, if you think a true positive is, that is good. You're telling someone that their well is polluted and they shouldn't be drinking from it. If you give someone a false positive, I knew I'd lose. I'd have to think about what these are under pressure. You're telling them that it isn't safe to drink from when it actually is. Which is, how do you really identify the harm in that? Because now you're taking away someone's drinking source. And, better safe than sorry, maybe, but maybe not, I don't know. And then a false negative, you're telling someone that it's safe to drink from a well that actually isn't safe to drink from. And although this is going to happen in an expert system too, how can you really identify the harm you're doing there? As machine learning experts or as data scientists, I just don't think that's something we're qualified to do. And what really made this hit home for me, and why the brief for this talk includes, and maybe we're thinking about this with a colonial mindset, is I was talking about adherence. And I was thinking about if we can just get these people to stick with the model, then we're going to be saving these, however many it was, sorry for the flashing, 329,000 people. We're going to be giving them the benefit. They just need to follow the model. But then this write-up by David Castelvici, also published in Nature, made the case okay, so imagine if you had a black box model that could tell you whether or not you're likely enough to develop serious cancer throughout your life, that the right thing to do is to preemptively remove the body part from which the cancer would be sourced. And this is what made me think, I don't know if I would cut my body parts off because a black box model said, yes, you're someone who should do that. Even if the accuracy was 95%, you know, if you compare this to if a doctor said this is something you should consider and they can explain it to you and you can reason with them, maybe that makes a bit more sense. And yeah, when you start, like I've talked about adherence, we got a window into how complicated these kinds of issues are with the vaccine rollout, where getting people to agree to take the vaccine was, you know, a really, really big part of the challenge. And for some things, we as data scientists can say there are acceptable boundaries. How, with my spam filter, how many times must it correctly identify spam? With my, and how many times can it incorrectly identify spam? And they say like 99% of spam must be found, 0.1, you know, these are just Google numbers. For speech to text, this was from a Microsoft webpage, which I did have linked, but I think the link's gone now. Anyway, they decided that high accuracy is less than 10% word error rate, and medium accuracy is less than 30% word error rate. So with these things, where you can just try it and try again, and all my emails ended up in the wrong place. Oh, it said about instead of about. Like, you know, it's really low stakes, and you can just keep trying it again until you get it right. With these deployments of like these vaccines or clean drinking water, you need to get it right first time, and you need to. I can't explain the complexity of it, but I've looked into it enough to determine that it is just horrendously complex. So that's just what I'm trying to illustrate with this section. So one relevant example that I'm sure you're all aware of is everyone says like, oh, when will machine learning models ever be able to identify cats from dogs because we as humans find it so easy? I don't know if they can still not do this or not. I don't think anyone really knows. We've all just, I think, collectively got on board with the idea that, oh, they can't do this anymore. But I bet if you did look it up, which I should have for the talk, but I didn't, by the way, they'll be pretty good at this point, I think. But this is still funny. And until this joke goes up and no one gets it, I don't think we're going to be able to really understand how long it takes for people to adjust to a model being good enough when it previously wasn't good enough. So yeah, how much did my machine learning models outperform the expert system models? Probably a lot, right? No, they actually, even though I imputed the data that the expert system models expected to have, which puts them at a disadvantage because they're expecting to work with this data, they still got an F1 score, which is, we explained the flaws of accuracy earlier. An F1 score is like a single-digit metric, which is an alternative to accuracy, which is better in this case, I would argue, and I wrote that in my dissertation, so I have to really believe that it is a better choice. So models 3, 4, and 5, those were the expert system models, and they outperformed even the worst performing one, any of the models 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, there's no 12. 12 was going to be an ensemble model, and it was a disaster. If you want to see some bad Python code, look at the repository behind this dissertation. But only that model. Yeah, the crazy thing is, I went into this field, and then not understanding the application of expert system models and just ignorantly thinking that machine learning would, by default, be better, and then those expert system models beat me at my own game. Outrageous. So at first, my initial instinct was that I wanted to beat them and I didn't. It felt like a failure. But actually, when I wrote it up and submitted it and cooled down, took a couple of weeks off, there were two things that I realized, and that was that we've contrasted the existing models with machine learning, and that's knowledge, and now we know what that comparison looks like. We're bridging this gap that was written about in the paper I referenced earlier in the talk about does geoscience have a lack of machine learning knowledge? And we have put a test train split on the arsenic model, so although we're saying they don't necessarily need this evaluation because no amount of accuracy is ever good enough, it's still an additional accolade for them, and it does show that they can stand up under this style of scrutiny that's not even within the field they're within. And I also made a Python interface for the expert system models that I converted to JavaScript, which I don't know if I can call a win or not, but there's a common framework between machine learning and the arsenic models now. And This was model 9, and we found that it was continuing to improve when we made it really, really, really big. But the problem is that we're trying to put 800,000 data points into this neural network, and it takes absolutely ages to train. So I think supervised learning neural networks are somewhat viable. They got like better performance than nothing, and they are continuing to improve with scale. But I think there's another project in this where we start looking at convolutional neural networks, and this is because we're putting the whole 800,000 rows into this neural network and expecting it to be able to deal with all this information at once. So a map, a data point on like the northernmost point of Bangladesh and southernmost point of Bangladesh are considered by the model together, and it just says these two don't interact with each other. If you had a convolutional neural network, you could just look at a window at a time, and I'm trying to get a dissertation student to take it on, but the year's already started now, and I think I realized that this was a good project a bit too late. So, last slide, I'll keep it quick. I realized that you can go into interdisciplinary things being way more open-minded. You can take the fundamentals you have from, for me, it was data science, and you can say, actually, maybe we don't need a test-train split, even though that was really reinforced in my beliefs. And, you know, you should trust the work other people are doing, because often if it doesn't look right to you, you may just not understand it, and just offer every good bit of yourself that you can to the project, but don't force any of it, and hopefully you can all get together and pick the best bits to make a good interdisciplinary project. So, people down the side have been trying the model. I hope you felt the suspense. I was trying to convey suspense when you went through each page, and it says, oh, you've got a prediction, and then up here, it's telling you, like, that guy got a false positive. We told him that it wasn't safe to drink from when it actually was. And I want to show, like, a survivorship bias. So, like, most of the time it works, but are you happy to take the risk of being one of these people who got the false negative, and how do you feel about giving them that false information? And that's really the knowledge I'm trying to convey in this talk. It's like, it's not really, there's never really an okay amount of people to tell to do a harmful thing. And that's the end. I think we have time for questions, but I know you have time to add me on LinkedIn and GitHub. So, yes, thank you very much for listening.
Thank you, Kane. We definitely have time for questions. One there.
So you mentioned during the talk that when you were evaluating the models, you did assign both a false positive and a false negative -1, true +1. You mentioned that you didn't have access, that you didn't feel comfortable tuning that curve. Was that due to a lack of access to experts, or is this an open, sort of unsolved question within the community?
It's not. The information isn't out there, I don't think. I think when you have a black box model, people can't make a informed decision on whether or not they should trust what the model has said. So I'm thinking of it in +1, -1. The point is that there's no way to tune that. But with an expert system model, or just an expert in general, you can empower people to make a decision for themselves by giving a decision and backing it up, which will never happen with a black box model. Any others? Yes. Thank you everyone for engaging in the demo, by the way. I wasn't sure how that would go. Thank you very much.
Were you able to scrutinize the model and see if it had identified any factors that the expert system didn't consider?
Oh, yeah, I did, and the expert system model beat all the other models in like every way. So model 12 didn't exist because the ensemble model looked at that. Do any of these models perform better where the expert system models perform worse? And then can we put them together and get the best of both worlds? And no, those expert system models annihilated all the models I made in every way. So yeah, thank you for asking. No, genuinely, thank you, yeah.
We have no questions. Hands. The talk was very, very clear. Let's do another round of applause. applause, please.